Good afternoon. My name is Biljana Antunović, and I'm professor of physics at the University of Banja, Luka. Today I will speak about building physics for energy efficiency, and here is the outline of the lecture. So let's start with the explanation why building physics. Energy efficiency of buildings became an important issue in the time of the world's energy crisis in the 70s. And as the consequence, energy price was higher, what caused a reduction in energy consumption for heating and cooling of buildings. In the 21st century, the largest amount of total energy consumption in the world is still used in buildings. Furthermore, the energy required to maintain a comfortable temperature inside the building accounts for 40 to 50% of global CO2 emission. Why building physics? The physical processes which continuously take place in the building envelope are hygrothermal loads due to heat, air, and moisture transport. If the building structures are exposed to large temperature differences and accumulated moisture, its impact on the building, users' health, and environment will be hazards. Buildings which do not have adequate thermal protection have increased energy consumption for the heating and cooling, which further leads to increased CO2 emissions, causing significant economic maintenance cost and thermal discomfort. For energy efficient and healthy buildings, it is important to use adequate thermal insulation, thermal mass in the building envelope, and optimize air tightness. Applying building physics, the processes can be explained and the performance of the building constructions predicted. In case of insufficient building documentation, or in case of old buildings, the measurement of building physics quantities must be performed. Building physics becomes an imperative, not only on the engineering task list, but on the global world agenda. Let's now say a few words about physical processes through the building elements, starting with the heat transfer. The difference in the interior and exterior air temperatures at the boundary elements of the building lead to an uninterrupted process of heat transfer through the building envelope from higher to lower temperature. In the winter, when the outside air temperature is lower than the air temperature inside the building, there is continuous heat transfer to the envelope, and in this way heat losses occur. In the summer, when the temperature of the outside air is higher than the temperature of the interior air, due to increased solar radiation, significant heat gains can occur within the building. Heat transfer through the envelope occurs via three processes: conduction, convection, and thermal radiation. Thermal conduction is facilitated by microscopic particles without bulk movement of particles, occurs in a solid, liquid, and gas. The density of conductive heat flow rate is proportional to the negative temperature gradient according to first Fourier's law, which defines a steady heat transfer via conduction. The proportionality coefficient is called the thermal conductivity. It depends on the density and the content of the moisture in the material. The specific thermal capacity is the measure of heat accumulation capability, storage of thermal energy. The larger are the specific thermal capacity and the density of the material, more thermal energy can be stored in the material. Convection is the heat transfer by moving groups of molecules of fluid from the region of the higher temperature to the region at lower temperature. According to Newton's law of convection, the density of convective heat flow rate between fluid and surface of a solid body is proportional to the temperature difference. Proportionality coefficient is called convective surface film coefficient. Thermal radiation is the transfer of heat by electromagnetic waves emitted by all objects with a temperature above absolute zero. According to Stefan Boltzmann's law, the density of heat flow rate emitted from the surface at the absolute temperature is proportional to the fourth power of that temperature. Epsilon is the emissivity of the substance or radiating surface, and it's calculated as the ratio of the energy emitted from a certain material to the energy of an ideal emitter. The density of the heat flow rate transferred by radiation between the air surrounding the building element and the surface of the element can be calculated using a similar formula as we did for convection. Finally, taking into account radiation and convection, the total density of heat flow rate can be calculated using this formula, where we see that alpha is surface film coefficient, in which we have contribution from convection and radiation. In everyday practice, all three types of heat transfer occur together. First, we have convection and radiation, which occur from the internal air in the room to the internal surface of the wall. From the internal surface of the wall to the external surface of the wall, heat is transferred by conduction. And finally, convection and radiation are again processes via which heat transfers from the external wall surface to the external air. Taking all these processes into account and solving set of equations, we get the density of the heat flow rate given by this formula. As we can see, the density of the heat flow rate is proportional to the temperature difference of the internal and external air, and it's inversely proportional to this factor. The denominator here is called the total thermal resistance of the flat wall. Its reciprocal value represents thermal transmittance, or the U value. U value is the amount of heat transferred to the unit of surface in a unit of time through the building construction element from the side of the warmer to the side of the cooler air when the difference of their temperatures is 1 Kelvin. The lower U value is, or the greater is the resistance, the lower the density of heat flow rate that passes through the wall. That means that wall is better insulated. The heat losses of the building through the transparent elements represent a significant share in the total heat losses in the winter and might cause overheating in the summer. The U value of a window is calculated using the following formula. As we can see, it depends on the thermal transmittance and surface of glazing and frame, as well as the linear thermal transmittance of the junction between the frame and glazing. The heat loss can be reduced using windows with multiple low E glazing, which means low emission, filled with an air or gas gap between the glass panes, and using frames with multiple chambers. The heat loss from the building is proportional to the temperature difference of the internal and external air. The proportionality coefficient, as we can see, is the sum of the transmission and ventilation heat loss coefficient. Ventilation heat losses constitute a significant share in total heat losses and occur due to infiltration and ventilation. The coefficient of ventilation heat loss can be calculated using this formula, where a rho multiplied by C is constant, and V is the volume, and N represents the number of air changes. The transmission heat loss occurs due to heat transfer via conduction, convection, and radiation, as we have already mentioned. The coefficient of transmission heat loss can be calculated using the following formula. As we can see, we take into account all building elements which constitute the envelope, and in addition, this transmission heat loss we have to correct for additional heat loss due to existence of thermal bridges. Thermal mass is also one of the important aspects when we speak about energy efficiency and building physics. Heat accumulation is the property of an element of a building structure to accumulate or store the heat. This property of the element is called thermal mass. It can be quantified with two physical quantities, the time lag and the decrement factor. The time lag is the difference in hours between occurrence of the amplitude of the internal and the amplitude of external temperature, while decrement factor is the ratio of the amplitude of the internal to the amplitude of the external air temperature. It is characteristic that massive building elements have large time lag and lower decrement factor than thinner elements of lightweight materials. Therefore, we are placing the thermal insulation on the outside part of the wall in order to have an adequate thermal mass of a building element. An important problem in buildings, apologize, which causes more than 70% of damages of buildings is the moisture. The moisture transfers into building constructions if they are in direct contact with water or water vapor. And there are three physical mechanisms of water transfer. Today, we will discuss condensation of water vapor diffusing to the construction. The consequences of transport and retaining moisture in buildings are different. Increased thermal conductivity, the appearance of the salt in the walls, the consequences on the health and comfort of users, additional mechanical strain on the structure, and by knowing physical laws describing the mechanisms of moisturizing building component, the waterproofing properties of the building materials, advantages and disadvantages, the most optimal ways of protection against moisture can be chosen. Water vapor diffusion is a spontaneous process of moving water vapor molecules from the region of the larger to the region of the lower mass concentration. It can be expressed using the gradient of the water vapor pressure and the first fixed law, which states that the density of water vapor is proportional to the negative partial gradient. The water vapor resistance factor represents the ratio of the diffusion coefficient of the air layer and the diffusion coefficient of the construction material of the same thickness at the same temperature. It determines the hydro-insulating properties of the material and depends on its structure. During water vapor diffusion to the wall, we consider water vapor transfer from the interior air to the layer along the surface of the wall, then diffusion to the wall, and finally water vapor transfer from the outer surface of the wall to the outer air. Solving the set of equations which describe these processes, we get a density of water vapor flow rate through the multi-layered flat wall. It's proportional to the difference of partial pressures of internal and external air, and inversely proportional to the water vapor diffusion equivalent air layer thickness. We can calculate this quantity as the product of the thickness and water vapor resistance factor. Condensation usually occurs in the winter period in structures where a sequence of layers of embedded materials, taking into account their thickness and the conductivity of the water vapor, is not adequately chosen, as, for example, the thermal insulation material is placed on the inner part of the wall. It's determined by calculation that the water accumulated during the humidification period of the structure will dry out during the summer or evaporation period. In this case, we consider that condensation is allowed. If it's not the case, then there are needed some design measures and changing of design documentation. Therefore, building components should have good thermal protection, thermal insulation on the outside part of the wall, and the surface temperature should be higher than the temperature of the dew point. The dew point is the temperature at which the water vapor condensates. At that point, the relative humidity of the air is 100%, and the partial pressure of the water vapor is equal to the saturation pressure. Condensation of water vapor might occur inside the building construction element or on its surface. In the case condensation is on the surface inside the building element, or so-called interstitial condensation, it occurs when saturation pressure line and the partial pressure line intersect at one point when we have condensation in plane, or more points when we have condensation in zone. The condensation site and the amount of condensated water vapor inside the building component can be determined using the Glazer's analytically graphical method. Surface condensation occurs on the surface of the building component when the warm air in the room collides with the cold wall surface. At places in a room where there is sufficiently low surface temperature, which means the dew point, surface water condensation may occur. The temperature of the dew point indicates the temperature at which the maximum saturation of air is achieved, and relative humidity is 100%. Condensation of the surface of the building component is an important issue when we speak about building physics. And one of the criteria which must be kept independently of other requirements is minimum thermal resistance, which can be calculated for any building component. The thermal performance of the envelope has large impact on the total energy consumption, as we have seen, the economy of the building, and the environmental protection. The methods which are recommended for calculation of physical quantities given in standards and used in the national regulations are largely based on the assumption of an ideal construction, although some minor corrections of the value are predicted for certain cases. The problem that engineers face is missing or incomplete design documentation. Another problem is that the construction materials might change their properties with time, for example, due to the moisture present in porous material. Therefore, measurements of thermal characteristics of the envelope should be performed. Thermal imaging is the qualitative, contactless, and non-destructive method measuring the surface temperature of the object by measurement in the invisible part of the electromagnetic radiation spectrum. It's used to detect thermal defects and their leakages in buildings or actual building envelopes. And as the result, we get a thermal image. Here we will show measurements for two buildings. For new building, there were no serious problems observed, but for the old building, as we can see, there are two different problems. There is moisture present in the building, and therefore there are defects in temperature distribution, and also there is increased infiltration of air. In accordance with international standard, U value can be calculated under assumption that sequence, thickness, and structure of used materials are known and that construction is ideal. The measurement of the U value on site and under actual conditions in which building is used takes into account different irregularities and the degradation of the structural elements. For some older buildings, the problem are thickness and thermal characteristics of embedded materials are incomplete, or the properties of the material characteristics have changed over the time. Here are the measurements of U value for two different buildings, the old one and the new one, which is energy efficient. As we can see, for the energy efficient building, the measurements of U value are in quite good agreement within the error. However, for the old building, measured U value is approximately 28% higher than design value is 28% higher than the measured value. The reasons are the age of the building, and the completeness of the information stated in design documentation. Another measurement which can be performed is the testing of air tightness of the building using the blower door test. The blower door test examines the object's air tightness and reveals imperfections in the thermal envelope, such as poor installation or poor quality of built-in windows and doors. The device achieves a difference in pressure, internal and external air of 50 pascals, and by measuring the volume flow of air, determines the number of air changes. Again, for two representative buildings, we have measured the air infiltration, and for the new energy efficient building, air tightness was satisfactory according to rule book requirements, which prescribe the highest permitted value for buildings with natural ventilation. For the old building, this was not the case, and measured value is about 3 times higher than it should be. Conclusions. In order to have an energy efficient building, increase comfort of users, and protect the environment by lowering CO2 emission, building physics plays an important role. Applying building physics calculations and performing building physics measurements in real conditions while new technologies and materials are used, the most optimal solutions for energy efficient and sustainable buildings, excluding hazards to the health of users, building materials, and the environment, can be found. In the 21st century, the energy efficiency of buildings can be improved using modern materials, which meet building physics requirements with significantly lower thermal conductivities and thermal mass, which is appropriate in order to reduce energy consumption. In case of old buildings and incomplete design documentation, measurements of building physics quantities must be performed. Thank you for your attention.